So hello, today this lecture will highlight some of the updates to the final project for winter 24-25. Please make sure that you have also watched parts 1, 2, 3 of the final project recitation because this will only highlight some of the new developments, which means some of the other details you will have to get from the previous videos. So first of all, the final project is worth 30% of your overall grade, and it will involve several navigation competencies. There are 9 competencies of varying levels of difficulty. Student teams select which competencies to complete. Each competency is worth a certain amount of points. For full demonstration points, the number of points must sum to 15. If it goes over 15, you can get bonus points on that. And for each competency completed, teams must submit in the final report a software design plan for that competency in the appendix, code in the appendix, and a discussion of the method, the results, and the conclusions. Project code is going to be worth 10 points, which is 6% of your overall course grade. Demos will be worth 15 points, which is 9% of your overall course grade. A software design plan for each of the competencies is 5 points, which is 3% of your overall grade, and the final report is worth 20 points, which is 12% of your overall grade. So the learning objectives include using reactive control to do light tracking, hybrid control to do wall following, path planning, and light docking, wireless communication to teleoperate a robot, wireless communication to receive data from a robot, creating a graphical user interface to send data to the robot, and display data received from the robot using a range sensor feedback to path plan, using range sensor feedback to path follow, using sensor feedback to localize a robot in an artificial world and plan a path through it. That's also called the kidnapped robot problem. To use sensor feedback to create a mapping algorithm for a robot, and then for the robot to plan a path through that map, and use sensor feedback to create a SLAM algorithm where the robot wanders around the world, finds a beacon, and then plans a path to exit out of a maze. For the light tracking part of the project, you should mount photoresistors on your sonar sensor mounts that face straight ahead, one over the left wheel, one over the right wheel. And then you will create 4 Bratenberg vehicles: love, explore, fear, and aggression. And note that you have to put a 10 kilo ohm resistor in series with the photoresistor to create a voltage divider, and then use analog read to read variations in that voltage as you shine a flashlight at the front of the robot. Here are the examples of the 4 behaviors. And here's an example of the 4 again, moving and reacting to the light. Once again, it's fear, love, aggression, and explorer. And here's a video that we can view later on YouTube, so we'll skip that. And then you'll create a software design plan. For the final project, you are given autonomy into what kind of software design plan you want to create. We've talked about several. You could do a subsumption architecture, you could do a flow chart, you could do a state machine, you could include a state transition table, you could do pseudocode, although I do not recommend pseudocode because it's probably the least helpful when designing a system, but it's your choice. You can have a different software design plan for each navigation competency that your team decides to do, but you must have one for each thing that your team does. So here's an example of subsumption architecture with reactive control, where the robot is tracking towards a light, but then if it sees an obstacle, it runs away for an obstacle. So obstacle avoidance becomes a priority over tracking the light. But then if the robot avoids and loses the light, it goes into random wander, or if there's still a light, it tracks light. And you can watch the video. Examples of light tracking. So then the next part of the final project is to now add on hybrid control, which means you're now planning a path to a light beacon, and also you are going to keep a track of how the robot gets to the light beacon so that it follows that path back to the wall to continue wall following. So here's an example of what hybrid control looks like, where you have a planning layer on top and a reactive control layer, sense act on the bottom. So it's a delivery layer on top, reactive control layer on the bottom, and that middle layer is like an arbitrator that moves back and forth, where the homing on the light and the wall following are reactive layers, while the path planning and then following that path back to the wall are the deliberative control. Videos for you to watch later on that. And then you're going to create a software design plan for hybrid control architecture. And wireless communication is the next part. So if you want to do any kind of remote control of your robot, you have to have wireless communication. And so the Arduino Giga has the capability of doing wireless communication already. You just have to look at some of the supplementary documents that I have put in the final project folder for guidance on how to do that. And you could do teleoperation with either your laptop or with the PlayStation controller, Wii remote, etc. So you can watch this video to see how to do that with a PlayStation controller. That's for remote control or teleoperation. But then also to get the data back, you can see how to do that. And then you have to create a software design plan for that part as well. Next part is to design a GUI or human robot interface in order to communicate remotely with the robot. The GUI is for you to get sensor data and status of your robot, as well as to send data, like to send a path or to send drive commands to your robot. And also to display a map or display how the robot localizes if you decide to do those parts. So you can make a GUI in any number of resources. There's lots of online resources for that. You can use MATLAB, Java, Python, processing, whatever you've learned in your previous courses. And here's a video of students demonstrating their GUI. You can watch that later on YouTube. And so you'll submit for this part a mock-up layout of the GUI and the information that will be displayed about your robot on your user interface. Things like how do you connect, map data, path data, sensor data, localization, robot state. How do you teleoperate the robot? And maybe you have arrows or controls for driving the robot. Whatever you think the GUI is going to need for a human to be able to remotely control your robot and get information from that robot. So a map can be represented as a configuration space. This is in the previous video, so I won't go into a lot of detail here. But here are some examples of the test bed that we typically build. It's a 4x4, 18-inch by 18-inch cells that can be represented as a matrix and also as boxes that are either filled or empty. Notice we have two types of encoding because sometimes you're going to have walls along the side. And the encoding we use is binary, where these numbers represent having a north, south, east, or west wall. So 0 means no walls on a cell. 1 means there's a north wall. 2 means there is an east wall. 3 means there's a north and east wall. 4 means there's a south wall. 5 means there's a north and south wall, and so on. So this is typically what you would use to represent a map inside of your code. And then you would process that map in order to get the data you need for your robot. So this is an example of that encoding on the test bed that I showed you in the previous slide. Topological path following. You now use the topology of the world in distinctive places to send the robot from a start to a goal position. So in other words, the robot is following center, making a Voronoi diagram, or following left or following right. And as it gets to an opening in the world, you have given it a path, so it knows that at the first opening, turn right, at the next opening, turn left, and at the next distinctive place, stop moving, which is that dead end. And here are some examples of that for you to view later. And a software design plan. An occupancy grid has 0s and 99s. You should also look at the reading to see how occupancy grids work. Metric path planning uses wavefront propagation in order to plan a path. It's like an A-star or D-star search of the map in order to determine the path the robot should take and then to give motion or movement commands to the robot, where it counts down from the goal. So it calculates how many steps from start to the goal, and each cell movement is trying to move down one step. You can either do 90-degree movements, or you could do 45-degree movements where the robot can move diagonal, but you have to be careful of obstacles or maybe grow obstacles if you are going to move diagonally. And here's an example of an occupancy grid cell where 0s is the start, 9 is the goal, and the 9 is the start, 0 is the goal, and then 99 represents an obstacle and all of the ways the robot can count down to get to 0. So here's an example of metric path planning using a human-robot interface, or a GUI. You should review that later. And the software design plan. Next, you're going to use sensor feedback in order to get feature extraction in order to create a map. So when you localize or create a map, you have to have a way to represent that data. So you can do that either as an occupancy grid or by a topological map, as I've described, by using the sensor data. And to localize, the robot figures out in how many steps will it be able to figure out how to get from point A to point B. And so what you're going to see in this figure is it could either be here or here. That's a 50% chance. Here or here, that's a 50% chance. But then once it gets here, this is the only place in the world that looks like that if the robot's orientation is known. So the robot would localize in 2 steps. In a 4x4 world, the robot should be able to localize in no more than 2 or 3 steps. And here's an example of localization with a GUI. You should watch that video later as well. And mapping. Mapping, you can either teleoperate the robot with your GUI, teleoperate the robot with a PlayStation controller or a Wii remote or a joystick. And then after the robot finishes, you can either plug your robot in and show the map on the serial monitor or wirelessly transmit that map back to your human-robot interface to display so that we can confirm that it is correct for you to get credit. And here's an example of the robot using a Voronoi diagram, and it is exploring the world, and the shadings represent how many times the robot saw that wall and the confidence level. Obviously, if it's an internal wall like here, the robot has to make a guess. 15 means it has pinged it enough times, it can confidently say a wall is there. 13.5, 14.5 means it's probably pretty positive one's there. But the darker shading, the more confident the robot is that it actually saw something there. Here's an example of autonomous map making. That's your other option where you have now programmed the robot to follow right and left until it has completely filled in the map. And it actually is not driven remotely at all, but it's using its follow center or follow wall to do that. And here's an example of map making with a human-robot interface for you to review later. And you have to create a software design plan once again for this portion. And finally is competency 9. This is the most difficult. This is the one I normally give to grad students. But by all means, feel free to try it if this is what your team would like to do. It's basically to use localization and mapping together at the same time. You've probably been doing a little bit of this already. So the robot is placed in a world, in an unknown world, and it creates a map of the world. And then a beacon is shown, which normally is a flashlight with a photoresistor detecting it. And the robot has to then transmit back where was the beacon. And now it's going to explore the world. And if one of the walls disappears, it has to figure out what wall disappeared, tell what wall disappeared, and then drive out of the map. And then you have to make a design plan for that. And here's a video of some students doing this slam from a couple of years ago. And the final report is discussed in the previous video, phase 3, so it would not be discussed at this time. If you have any more questions about your final project, please go and see your professor or the teaching assistant.